Hi everyone. So far we've been talking about DC current, and I want to now introduce a fact that is frankly impossible to anticipate. And that is the fact that if I have a line of current, a wire flowing in one direction, and I have another parallel line of current, those two lines of current will attract one another. Now, this really shouldn't be. There's no reason for it. Because even though we have the motion of electrons, that wire is electrically neutral. For every electron, there's a proton, a corresponding proton. The force that pulls those two wires together is not electrical in nature. It's something new. And therefore, it's impossible to anticipate. We call it the magnetic force. Now, usually when we introduce magnetism, we talk about bar magnets, and we will talk about bar magnets when we get to the point, but I think it's very important here to introduce the idea through this concept of parallel lines of current, because fundamentally when we get to recognizing why magnetism is the way it is, it has to do with the combination of electricity and relativity. And this is the situation in which it's most easiest to understand. Also, there are some significant applications of this fact. Now, the formula up here you won't need in the textbook problems, but that is basically a formula for how much force per unit length is experienced between the two lines of current. And notice the form is almost exactly the same as Coulomb's law, same as Newton's law, except it's R, not R squared in the denominator. And that really comes down to geometry. We're talking about a line of current, not a point charge. There is something called the Biot-Savart law, which is a closer parallel to Coulomb's law when we talk about a point of charge, but that kind of doesn't make any sense, because how could you have a point of charge? It has to move. It's got to flow. In order to have a constant current, you have to have a long wire. And so I feel this is a better way to introduce the concept. Again, it's not something you, strictly speaking, really need. But there are a couple situations which this is very important. This picture here represents a tube of metal that was struck by lightning. And you can see that it was crushed by that magnetic force, the sheer huge amount of charge that was flowing through. Remember, when charge flows through a conductor, it does so on the surface. So basically you had this ring, the cylinder of current flowing through this metal pipe. And because the flow of current is attractive, is magnetically attractive, it crushed that piece of metal. And so that's an interesting fact. It's also the main reason we don't have fusion power. Because there are several ways to talk about creating fusion power. One of them is through plasma. And plasma is an electrically active gas, and you basically put it in this ring, this donut, this magnetically confined donut, and run the plasma through very hot, run it through very quickly, and basically try to get the atoms, the nuclei to smash into one another and fuse the same way they do in the sun. The problem is that if you've got gas, electrically active gas flowing, it's exactly the same as this tube. And so that flow has a tendency to not just flow smoothly, but it wants to twist, curl, braid around in this very complicated fashion. And so, you start out with a very smooth pattern here, and, very quickly, you hit a threshold where all of a sudden the plasma becomes extremely unstable, and you can't support, the kind of cumulative effect that you're looking for in fusion power. And so, containing and controlling this plasma as it flows is extremely challenging, and it may not be possible from an engineering standpoint, but people are working really hard on it.